This is the video lecture for the How Statistics Lie to You lesson plan. It was created by Nathan Andre and edited and narrated by Sean Krupa. This video and accompanying lesson plan are part of Ohio University's Boat of Knowledge in the Science Classroom, funded by the National Science Foundation. Let's start by taking a look at a set of graphs. Take a few minutes to notice the similarities and differences between these two graphs. Hopefully, you noticed that the y-axis on the graphs are drastically different. On the left side, the y-axis only changes from 9 at its lowest to 10 at its highest. However, on the right side, the y-axis changes from 5 at its lowest to 10 at its highest. This makes the change in the pre-test to the post-test look huge on the left side while very small on the right side. So what's going on here? Graphs are a good way to give people a clearer idea of what a dataset means. Unfortunately, none of the infinitely many ways to graph a dataset is considered the right way. Some ways actually makes the graph look unclear or show things that are not true. Sometimes this is done intentionally. Here are two graphs of the same data. However, they look dramatically different. It's not important to know what these graphs represent, but you can see that by changing the scale, the changes in the graph look dramatically different. You would never use this graph on the bottom because it looks uninteresting. Changing the scale makes the changes look much more dramatic in the top graph, making it more eye-catching and suitable for a newspaper. Let's talk about how using a different scale can manipulate graphs. Most graphs you see will use a linear scale. This means that the same space on the vertical axis corresponds to the same numerical increase. However, sometimes it's useful to use a logarithmic scale to show trends. Unfortunately, sometimes different scales are used to mislead the viewer. Let's look at an example. Would you believe that the three graphs shown here are of the same data? Well, they are. On the x-axis, we have a number, and on the y-axis, we have that number squared. Therefore, each graph is a graph of x versus x squared. However, the scales on the three graphs are each different. Starting in the top left corner, we have a graph with linear scales on both axes. In the top right corner, we have a graph with a logarithmic scale on the y-axis and a linear scale on the x-axis. In the bottom center, we have a graph with log scales on both axes. Now imagine this data set were, say, the crime rate or the spread of an infectious disease. If you wanted to show that the problem was getting worse, you would use the graph in the top left corner. If you wanted to show that the problem was getting better, you would use the graph in the top right corner. And if you desired to show that the problem was the same now as when it started, you would use the graph in the bottom center. These are three graphs of the same data. However, manipulating the scale means you can use different graphs to support whatever story you're trying to tell. Now let's talk about how area is used to distort a graph. We've seen that altering the scales or the bounds can massively distort the appearance of a graph. Another way to do this is to use an image instead of a bar. Because the image has a constant ratio of height and width, the width will scale the same as the height, distorting the appearance of the graph. On the left side, we see a picture of a frog representing data. In reality, the right side of the graph is only supposed to be 3 times larger than the left side. But because they're using the area of a picture, the height and width of the picture both scale by 3. Therefore, the area increases by a factor of 9. This exaggerates the number of frogs. On the right side, we again see how changing the bounds of a graph can distort its purpose. Using the first bar graph, you would see a much bigger difference in the frog population from May to September than that of the bar graph on the far right. Similarly, let's look at this picture of fuel economy standards from the New York Times. From 1978 to 1985, the fuel economy standards only increased by 50%. But because of the way this picture is shaped, the area at the earlier times looked much smaller than the area at the more recent times. This would tend to cause people to think the change was much greater than 50%. Now let's talk about citing reliable sources. You can probably hear your English teacher right now telling you to cite your sources. But what's the point? The answer is bias. Some sources are reputable. Here's a graph, for instance, from the World Bank. Now here's a graph of the United States national debt, but it's from a website called endoftheamericandream.com. It doesn't exactly sound the most trustworthy. Here's another graph of the United States national debt. Let's talk about interpreting data. There are many different ways to interpret data, and whichever interpretation you use depends on what you're trying to prove. The graph below shows the national debt corrected for inflation. Suddenly, the problem doesn't seem as bad as the graph on the previous slide. Here's yet another graph of the national debt. This time, the national debt is represented as a fraction of the GDP, or gross domestic product. The GDP of a country gives an indication of how big its economy is. Therefore, if we have higher debt, but our economy is bigger, it's not quite as big of a problem as the previous two graphs made it out to be. So what did we learn from this? There are many ways to interpret the same data. Ultimately, a graph is just an interpretation of data and not fact. Make sure you trust the source of that interpretation. So, how do they get away with lying to us? There's two main answers. Most people have a really bad intuition for statistics. Also, people tend to crave an explanation. We like to know why things happen and what causes things to happen. Don't believe that your intuition for statistics isn't strong? Let's take a look at some examples and find out just how strong your statistics intuition is. Let's start with a famous game show, Let's Make a Deal. For those of you that are unfamiliar with Let's Make a Deal, here's the basic rules. A contestant chooses from 3 doors. One of the door has a fantastic prize behind it, while the other 2 have goats. After the contestant makes his choice, the host then shows the contestant what's behind one of the doors they didn't pick. Whenever the host does this, he always reveals one of the goats. The host then gives the contestant the option of sticking with their original choice or switching to the other unknown door. What would you do? Do you think it's to your advantage to switch? Do you think it's to your advantage to stick with your original choice? Pause this video to discuss your strategy now. Be sure to explain your reasoning. In the Let's Make a Deal game show, if you use statistics, it's possible to win 2/3 of the time. Let's assume that P is the prize while G is the goat. Given that the contestant will always pick a prize or one of the goats, the remaining doors will contain either a prize and a goat, or a goat and a prize, or if you get lucky and pick the prize originally, the other 2 doors will be a goat and a goat. Since the host always reveals a goat, we're left with either a prize, or a goat. That means if the contestant always switches doors, their chance of winning a prize becomes 2/3. However, when people play the show, they almost always stick with their original choice. The show's creators use this to their advantage. People are inherently skeptical. Now let's look at an example known as the double birthday party. Look around the class. What do you think the chance that 2 people in this classroom have the same birthday is? What if the class has 30 students? What if the class has 40 students? Take a few minutes and discuss what you think the chances are. Be sure to explain your reasoning. You might be surprised to know that in a class of 23 people, there will be exactly a 50% chance that 2 people will share the same birthday. If you increase the class size to 30 people, that becomes a 70% chance, and at 40 people, it's a 90% chance. Humans tend to be a bit narcissistic and only think of themselves. I bet when you were looking around the classroom, you thought, does anyone have the same birthday as I do? But you could apply this logic to every single person in the class. Therefore, the chances that 2 people in the class matching are much higher. The last example we'll look at is correlation and causation. Here are 2 graphs that I want you to study. In the top left, we see the sales of organic foods plotted with the diagnoses of autism cases. In the bottom right, we see the average global temperature plotted with the estimated number of pirates that exists on the planet. Do these graphs make sense to you? Can you explain them? Take a few minutes and try to explain the results. Be sure to explain your reasoning. Hopefully, most of you came to the conclusion that both of these graphs are completely nonsense. In the top left, we know that organic food sales are growing in popularity. However, completely unrelated to that are doctors are getting much better at diagnosing cases of autism. Whether or not the cases of autism are actually increasing remains a debate. However, it's not debated that we're getting better at diagnosing it. Secondly, we know that pirates have been increasingly diminishing from the planet Earth. However, we also know that the planet is getting warmer. The planet is getting warmer from the Industrial Revolution and man-made causes. Pirates, on the other hand, are disappearing for other socioeconomic reasons. Therefore, just because 2 things are happening at the same time does not mean they're causing each other to happen. So, the take-home is that correlation does not equal causation. Why is it so easy to fall into this trap? Humans evolved to recognize patterns. It's much easier for humans to believe that there is a pattern or a connection when there really isn't one. Using correlation to imply causation turns our human instincts against us. So what should you take home from all of this? A graph does not necessarily prove what it claims to, even if the data is real and legitimate. You can't trust every statistic you see, even if it comes from a reputable source. Sometimes our human intuition can be turned against us. The only way to fight against this is to learn statistics and interpret the data yourself so you can't be tricked. For more information, visit the links listed here. Thanks for your attention.